We've got a great panel tonight, and we're privileged to have them in. I personally want to say a big thanks to two of the panel tonight, Helena Gosden, who will be chairing the event. Helena's been involved with us as a principal sponsor for ARB from the outset, and she's just had so much enthusiasm and help and information that she's provided throughout the course of the planning of this show and programme of events. And likewise, a special thank you to Professor Dave Glue, who again, his expertise and knowledge has been invaluable throughout the whole process. So thank you for turning up again, and I'm going to pass you over straight away to Helena Gosden from ARBs.
Thanks very much, John, and welcome everybody. I'm delighted to chair the event this evening, Retrofit Meets Solid-Walled Homes. Solid-walled properties represent a significant proportion of the circa 28 million homes that we need to retrofit by 2050, and they also represent some quite unique challenges. So I'm sure that tonight's event will leave us all with a better understanding of what those challenges are and hopefully better equipped to address them as well. This evening, we will hear about the demonstration of Energy Efficiency Potential Project, using the acronym of DEEP, which is research funded by the Department for Energy Security and Net Zero. It's led by Leeds Beckett University in collaboration with the University of Salford and Loughborough University. The project is the largest of its kind ever undertaken in the UK, so I'm excited to learn a little bit more about it this evening. At the risk of stealing a little bit of thunder, I'm just going to share a little bit about the project content. The project provides case studies, laboratory and data modelling on safe and effective ways to retrofit solid-walled homes. It explores costs, benefits and risks, and the value of a whole-house approach to retrofit, including the implication of retrofit for air source heat pumps. For the research, measured performance is compared to models to understand the accuracy of predictions, including those made by Energy Performance Certificates, or EPCs. It also explores how assessments of performance and risk assessments can be improved. We're very lucky to be joined this evening by 4 representatives from the academic institutions involved here. They will be presenting in order that I will now introduce them. There are 3 Davids here this evening, so bear with me. Up first will be Professor David Glue, who is joined by Adam Hardy from Leeds Sustainability Institute. They will share their research findings with contributions from Professor David Allinson from Loughborough University and David Farmer from Salford University. Professor Glue is Director of Leeds Sustainability Institute. David manages large interdisciplinary retrofit evaluation projects and is an established expert in retrofit evaluation. He's been seconded into the government departments, previously BAYS, and is still often called upon for guidance on issues facing domestic energy efficiency policy and research. He's also a regular contributor to national and local media. David is joined by Adam Hardy from Leeds Sustainability Institute. He's a data scientist specialising in energy and sustainability data. Adam initially started his academic career in astrophysics, and he now specialises in the analysis of energy data, particularly those from domestic buildings, and uses data to estimate the environmental impact of our homes. From Loughborough University, we have David Allinson, a professor of building physics who leads the Building Energy Research Group in the School of Architecture, Building and Civil Engineering. His research combines measurement and modelling techniques to evaluate the energy, thermal and moisture performance of our homes. And finally, we have David Farmer, a research fellow at the University of Salford, where he manages the Salford Energy House. He's an expert in the measurement of building fabric and heating system thermal performance. David's undertaken research on a wide range of housing types and heating systems and in both the new build and retrofit sectors. So without further ado, I will pass over to David Glue and ask him to begin his presentation and kick off this evening's proceedings. But I would ask, please, of the audience for you to be thinking of some questions for the Q&A, which will follow at the end. Thank you very much.
Right, enough about us. You're not here to hear about what we do. We're very grateful to be here, not just doing this event today, but to be involved in the rest of the exhibits that have gone on for the Building Centre's exhibition on retrofit. When we found out that the Building Centre was doing an exhibition on retrofit, we thought, well, aren't we lucky? Because we had just done an enormous project on retrofit, and we've now got the medium in which to disseminate some of that to people. So we're really grateful to be involved. I'm just going to give you an overview of the entire project very quickly, and then I've got a bit of a day off because I'm really grateful to have the rest of the team to talk about the specific bits that each of them have been working on for what is a very long time. This project started in 2019. So just as a recap, that was before COVID. And most of the testing actually we were able to undertake during COVID, and I'm really grateful for the team for just sticking with it. We'd also should probably say, they're not necessarily here today, but thanks to the government. The government's actually funding this, so they are interested, and this was before Ukraine, this is before fuel prices went crazy, so it was something that we should be grateful for, that this sort of work was put into place a couple of years ago and is now hopefully going to make an impact on government policy. Okay, so the Leeds Sustainability Institute at Leeds Beckett University, we've got 3 research themes: sustainable behaviour, healthy choices, why do we make them, why don't we? Sustainable buildings, that's what this project is all about, we'll talk about what we do there. And sustainable urban environments, that's the people sit in the buildings and the buildings sit inside the context of the communities. So that's sorts of things that we do. So we've been doing this for a while, but our main focus today is just going to be on sustainable buildings. I'm going to talk to you about the research project DEEP, which has just been introduced, but as a bit of a background so I don't have to keep talking to you about it, I'm going to show you a video which we put together which just gives a bit of an overview of the sorts of key themes that we were looking at today. If you do get the slides, I don't know if you get the slides, but there's some QR codes for other retrofit projects that we've done, but we won't talk about them. We're going to go straight to DEEP. Okay, I'm going to press go and hope that this works. DEEP Retrofit project stands for the Demonstration of Energy Efficiency Potential, and the idea was to work out how much energy was saved when you retrofitted homes.
So this project was funded by the Department for Energy Security and Net Zero.
The project was one of the largest of its kind in the UK ever undertaken. Heating homes is responsible for a lot of the carbon emissions in the UK. Being warm in our homes is obviously very important for our health and comfort and our mental health as well. The coldest homes in the UK tend to be solid-walled homes. We were really fortunate to get 14 different houses that we could test these retrofits on. So we installed over 40 retrofits in those homes.
So we did a number of different tests. We did the co-heating test, that gets the overall energy efficiency of a building. And we also did surface temperature measurements.
You could make changes to one house and then see whether or not anything happened to the neighbouring property that didn't have the changes done to it, and also what the improvements were.
We tracked the changes in energy efficiency by measuring before we did anything, the baseline stage. Then we did the retrofit work, and then we measured all of those variables again, which allowed us to see the effect that the retrofits had.
Solid-walled homes can be at risk of having surface condensation, which is not a good thing to have in homes for mould growth and damp.
When you insulate that wall, you tend to make the wall much warmer, so you'll have less condensation in general on the wall. But it does get a bit complicated because even with insulation, the edges can be cold, so you can still get condensation there.
So this is really good evidence to supply government with to make sure that retrofits are installed safely in homes, and this is what the whole house approach to retrofit has been designed for. So what we were able to do in this project was compare the energy performance certificate predicted savings with the measured savings.
You might do an EPC and think there's loads of scope to do work to bring that number down, but actually your number was already quite low and the EPC got it wrong.
I think a lot of people understand the importance of retrofit, but don't understand what can go wrong and the unintended consequences of retrofit.
We understand more now about the risks of undertaking retrofits in a piecemeal approach, and we're providing more data to explain why it's very important to have a whole house approach to retrofitting homes. It's a bit cheesy, but it's all right. So there's a much more dynamic way of introducing the project than me talking about it. So you've heard a little bit there. trying to boil it down a little bit to more tangible things. Okay, what were the actual main goals here? So we think we've provided a lot of new information on how to decarbonise solid walled homes. So when we publish our reports, that's going to be one of the key findings, and we'll talk a little bit about that today. We're also talking about what you heard there, the whole house approach, and that's just a little bit of a quote about the whole house approach. We come across this a lot, and obviously it makes a lot of sense intuitively to think that the whole house approach means doing absolutely everything to a home. And that isn't what the whole house approach is. The whole house is thinking about everything so that you are able to install the thing that you're doing in consideration of everything else. So that's the key difference there. And then the government, and you all have EPCs for your homes, I'm sure. You all look at them and you pay a lot of attention to them. But these are things that are in use and things that are really important for government policy. So we were looking at how we could make improvements to the way in which they are undertaken, made more accurate. And we'll talk about that a little bit today as well. So the project is very big. You're only going to hear a little bit about some of the findings. We can't possibly give you an overview of everything. So 3 universities here. It was funded by Department for Energy, Security. We had some other contractors involved as well doing some of the testing, and we're really grateful to the housing associations who let us have their homes. We rented the homes, but they let us in, which is a really, really difficult thing to get people to do. So as I say, we started a long time ago. We are now just at the point of completing, and we hope to be able to publish the results very soon, not quite yet. So this is my last slide. This is just an overall reminder. We did some field trials at Leeds Beckett, so that's what Adam's going to talk to you next. Salford are going to talk about the test that they did, which mimicked what we did out in the field in a test environment. And that was really important. And then Loughborough University undertook some modelling work to complement some of the retrofit understanding that we were gaining on the field as well. Okay, so I'm going to hand over, I hope, to Dr. Hardy to come and talk about the field case studies.
Thank you for coming, everyone. I'm Dr. Adam Hardy. However, as I am preceded by David Glue and followed by David Allenson and David Farmer, you can call me David, it's fine. I'll respond to David Hardy if necessary. So I'm here to talk to you today about the results from our field work, i.e. our case studies. And as has been mentioned, the DEEP project was interested in what happens when we retrofit solid-walled homes. So the first thing to do is to introduce you to our sample of solid-walled homes. They're all pictured on the right here, and as you can probably tell, the majority of the homes are standard solid brick construction. For example, quite a lot of Victorian terraces. So we had 11 of those, but they weren't all like that. The home in the bottom left here, for example, was concrete. And the home in the bottom right was an interesting construction. It's a bit of a mix. It had the ground floor of brick and the upper floor of block, and it had some steel beams in there as well. So there was 2 which I've termed here as non-traditional. And we also had a really quite nice farmhouse in the middle with thick stone walls. This one is my personal favourite because that one was located in the North York Moors. Nothing else around, really quite isolated, and we were testing this house in peak COVID, so it's a really nice haven there from the chaos that was happening in the rest of the world. So add those up, and then we had 14 case study homes in total. So those are the homes, but what about the retrofits we did in the homes? We did 42 retrofits in total, comprising of 7 air tightness retrofits. That's where we went around and we sealed up any holes in the fabric that weren't really supposed to be there. Or, for example, we might improve draft stripping on doors and things like that. We did 4 loft insulation retrofits. Now, most homes will probably have some form of loft insulation in them already, but often that insulation isn't up to modern standards in terms of thickness, or if it is, it can be quite patchy because over the years it's been peeled back, or people have put things on top of that loft insulation, meaning it's not so good anymore. So in those retrofits, we made a nice standard layer of insulation. We also did 4 room-in-roof retrofits. This is where, if we had a room-in-roof room, we went up and we took away all the bits of wall and the sloped ceilings in those spaces, and we added insulation behind them. We did 5 lots of retrofits where we replaced the windows and sometimes the doors. Then we did 12 retrofits where we installed floor insulation. We did quite a lot of these because it was thought that floor retrofits might be something of an untapped market, and we were interested in what potential could be achieved if these were retrofitted en masse. We did 5 retrofits of solid wall insulation. 3 of those were fitted externally, so external wall insulation where you fit it to the outside of the property. 1 of them was fitted internally, and the final one was a hybrid where we did part of it with external wall insulation and part of it with internal wall insulation. And then the final 5 retrofits were what's called a whole house approach. This was alluded to in the video, but it needs a little bit of care taken because it is not going to a property and retrofitting everything at the same time. That is not the whole house approach. The whole house approach actually refers to having consideration about how different insulation products interact with each other. For example, often if you fit external wall insulation, that insulation won't reach all the way up the wall because the roof gets in the way, so you'll have a strip that's not insulated. A whole house approach would come in and fix that strip of insulation, probably by fitting some internal wall insulation. So it's about ensuring you have a consistent stream of insulation all around your property. So the attentive amongst you will note that if we had 14 homes and we did 42 retrofits, we must have doubled up somehow, and that's what we did. So a typical retrofit strategy would look something like this. We take a home that's had nothing done to it by us, and then we did a series of tests on that home. We would test its thermal performance by something called the coheating test. We would test its air tightness. We would do thermal imaging of the home. We would do a whole bunch of other tests, and we would also do lots of models of the home, and I'll come into that in greater depth in a bit. Then we would go ahead and have a retrofit done to that property. In this case, it was loft insulation first, and then we repeated all of those tests again. So we do a coheating test, our air tightness tests, everything. We do it again. Glazing retrofit, again, same. We repeat all of our tests. The floor insulation retrofit, and then finally, for this home, we did the solid wall insulation retrofit, again, repeating all of our tests. The order of retrofits, we tended to try and do them from kind of the most simple for the loft insulation to the most technically complex, on the basis that these are probably the ones that people are most likely to do, to the ones that people are least likely to do. And you can imagine if we were doing all of those tests at every stage for 14 homes, we gathered a lot of data, and that data was used to help inform the goals of the DEEP project. I'm going to just touch on 3 of the goals that we studied, but please bear in mind, we've only got 15 minutes, and this is a massive project, so I'm only going to be able to sort of scratch the surface. The first goal then was to study the energy-saving potential of those different retrofits. How effective is loft insulation compared to a room and roof insulation, for example. So to illustrate how this worked, we'll go back to that house I displayed just now. I'm going to look at the results of the coheating test. The coheating test gives you a value called heat transfer coefficient, or HTC, and that tells you how much heat loss you're getting from your property, so you want this value to be as low as possible. In the baseline case, when we hadn't done anything to the property, the value was 250, which is fairly high. And we then did our loft insulation retrofit, and it looks like it drops a little bit, but actually, these numbers are really close together, and statistically, we can't tell the difference. So there's not a detectable impact of doing the loft insulation. We did the glazing retrofit and found the same. We didn't detect an impact from the glazing retrofit. We did the suspended floor retrofit, and again, we didn't detect. Then we went and did the solid wall insulation retrofit, and there was a massive drop in HTC. So we went from 250 initially down to about 100. So although this is just one of the 14 homes, the story of this home is quite typical of what we found in a lot of the other homes. The easier retrofits, like loft insulation, for example, often didn't have a detectable impact on the heat loss of a property. Whenever we did solid wall insulation, whether it was internal or external, it did have a detectable impact on the heat loss. So from a policy perspective, if you want guaranteed reductions in heat loss, solid wall insulation is a pretty good bet. On to goal 2 then. We were also interested in the unintended consequences of retrofit. And when I say unintended consequences, principally here I'm referring to moisture. If you put insulation on some surfaces, you can cause moisture to build up, which leads to mold, and none of us want mold, so we wanted to make sure that isn't going to happen. To study this, we looked at the junctions in properties. The junctions are where, for example, the floor meets the wall, or the wall meets the loft. And we modelled those junctions, and we looked at the percentage of those junctions which have a moisture risk. That's what's plotted on this graph. So we're looking here at the homes that had the external wall insulation only, and the colour at the bottom shows which home it was. The percentage, so the first thing to note is that in the pre-retrofit stage, i.e. the baseline stage, the homes that already actually had quite a lot of junctions that posed a moisture risk. When you did various retrofit measures, the risk of moisture tended to decrease or potentially stay the same, but it didn't get noticeably worse. When you fit the solid wall insulation, in all cases, the percentage of junctions that have moisture risk did decrease noticeably. But the final retrofit, which was the whole house approach, is the final step to really minimizing your risk of having moisture on your junctions, which instinctively can kind of make sense. As I said before, if you fit your external wall insulation and don't quite do the top bit, you're going to have a nice area of cold wall where moisture is going to form. Your whole house retrofit would come and fix that, make it warmer, thus decreasing your risk of moisture. And the third goal then was to look at energy models, see if they're working as intended, and look for any ways that they can be improved. So energy models are pretty important because often they're used to assess how a property is performing and therefore what retrofits you might want to put into that property. And we're going to assess sort of various energy models on this graph. On the x-axis is the co-heating HTC, so that's what we measured for the thermal performance of a property. On the y-axis, I'm going to plot the modelled HTC from a series of different models. And if the model is spot on, in agreement with the co-heating test, it's going to fall along the black line, so that's what the models ideally want to do. First model to look at is that generated by energy performance certificates. You're probably all aware of these, as your home probably has one, and they are often used to inform retrofits, in fact, but they consistently predict HTCs which are higher than that which we measured. This has, furthermore, actually, the disagreement between the EPC HTC and the co-heating HTC is worse for poorer performing properties. So this has potential implications if you're going to use EPCs to perform retrofit, because A, they're probably getting your heat loss number wrong in the first place, and if you're in one of the poorer performing properties, that difference is even worse. So EPCs are quite a blunt tool anyway, and built into them is lots of assumptions about how your property is behaving. So we wanted to see if EPCs could be improved by changing those assumptions to be more realistic. So we sort of broke into the software to change those assumptions, and we used a tool that was developed by the BRE, so I'm going to use the BRE logo here. And by changing those assumptions, the results did improve in that they've dropped down to be closer to the black line, but still they're quite far away, and they still show the same pattern of being worse for poorer performing homes. So it's potentially not just an issue of assumptions that are flawed within the EPC models. There may be something in the algorithm itself, the system of the making EPCs, etc., that could do with some tweaking. To determine if models can kind of ever accurately assess the HTC of a property, we put these two to one side and created independent models that were really quite complicated. So we did these in Design Builder. We built the whole house in a computer, basically, and modeled the heat loss through every single junction. We modeled how the sun is going over that property and a whole host of other things. And that's what the orange points are showing. And indeed, it got pretty close to the black line. So the conclusion from that could be, use Design Builder, it worked really quite well. However, it's really, really time intensive and needs a lot of expertise to use Design Builder, so that's probably not practical. The optimal solution for modeling could lie somewhere maybe in between these two. To conclude then from these 3 points, the only retrofit measure that achieved measurable differences consistently was solid wall insulation. So if you want to achieve considerable savings, that's potentially one to focus on. The moisture risk generally does decrease with retrofit, but if you really want to decrease your moisture risk, the whole house approach is excellent for doing that. And standard EPCs are very often wrong. You can make some tweaks to make them a bit better, but it only goes so far. So that should be considered when people are using them to plan their retrofits. That's all from me, and I'm passing over to David Anderson. Thank you very much.
Thanks very much. I want to talk to you about the risks from moisture and overheating. But first of all, I just want to talk about numbers. So I'm a building physicist. I love numbers. Any numbers fans in the room? A couple, tough audience. Good. A few more. Thank you. So I love numbers, and I'm surrounded by numbers. And here's a few numbers that I took from objects that are in my house as I was looking around my house. There's two of these that I want to pick out as being particularly interesting from my perspective. The first one is this. It's the specification for a temperature sensor. I do lots of temperature measurements, and temperature sensors often come with a plus or minus figure at the end. That shows their uncertainty. How accurate is that measurement? What's the kind of error that you might expect in it? Uncertainty is really important to me as a building physicist. And this one at the bottom, 10,000 millimeters hydrostatic head, I don't know if anyone knows what that is. But I love walking in the mountains, and that's the rating of my waterproof jacket. So you can't sell a waterproof jacket where you say it's waterproof or not waterproof, because actually there's no such thing as waterproof. It's really difficult to do. So what they do is a lab test, and a 10,000 millimeter hydrostatic head waterproof jacket is better than a 5,000 millimeter one. And so you can use that to compare waterproof jackets and pick the best one. You get what you pay for them. There's another type of metric in my house that I'm less fond of. First of all, it's not very good, I'm afraid. But secondly, it's got some problems with it. And I want to talk a little bit about problem metrics and the curse of uncertainty, as I'm going to call it. And one of the problems with EPCs is they're based on running costs. And that's sort of tricky because the running cost for your house is going to depend on how you operate it. It's going to depend on the weather, and it's going to depend on the cost of fuel. So when my EPC was generated, the cost of fuel was nothing like it is right now, and no one could have guessed that. So that metric's a bit dodgy, I would say, because of some of the assumptions that underlie it and the uncertainty in those assumptions. There's two other dodgy metrics I'm going to mention. One is overheating risk, which is pass-fail. In the way that we assess this in official documents, it says that temperature must not exceed some threshold for more than so many hours. And it's the same with moisture risk. Again, it's a pass-fail metric. It's like saying my jacket is waterproof or not waterproof. It says that the relative humidity levels at some critical junction must not exceed 80% for more than a month. Well, that's one of the ways that it's assessed. The problem with these pass-fail metrics is if you have a temperature relative humidity profile against time, and you put some threshold on there, well, what if there's some error in that measurement? Or what if there's some error in that model that's created that profile? Maybe the model is actually the true value is a bit lower than that value, in which case it's safe, you needn't worry. Or what if the uncertainty in that means it's a bit worse than that value, in which case it should actually be a fail. So pass-fail metrics are really problematic. What would make a good metric? Well, it should be predictable, useful, and comparable. It's going to help you make decisions. Should I do this or should I do that? Is this thing better than that thing? For my waterproof jacket, I want the 10,000, not the 5,000. And what about uncertainty? Well, it's always present, it's often hidden, we don't like to talk about it, and it's maybe too scary. Someone in a government department once said to me, there's no such thing as uncertainty in policy. And that sort of struck me as a scientist, because uncertainty is fundamental to everything we do. So how do we communicate across that divide? So at Loughborough University, we were tasked with answering two questions, myself and my colleagues here. Does whole house retrofit increase the risk of overheating? And does internal wall insulation increase the risk of interstitial condensation? So Adam was talking about surface condensation on the inside. I'm talking about interstitial between the layers of the fabric, that hidden moisture risk. So the first thing I thought is we need better metrics that are robust to uncertainty, simple to use, and easy to communicate. And you're my guinea pigs. I'm going to see if I got that right. And you can tell me at the end. So the first question, does whole house retrofit increase overheating? So we used TM59, dynamic thermal modeling approach. If you don't know what that is, don't worry. It's something that's used in the building regulations. It's like a standard way to run models to say whether they overheat or not. We did it for two types of home. The top one is it's like a semi-detached where you can cross-ventilate. Ventilation is really important for mitigating overheating. And the bottom one was a back-to-back terrace, so you can only single-sided ventilate. You can't open windows on both facades to get the wind through. We looked at 3 locations before and after a whole house retrofit, and we looked at simple mitigation strategies. What if people opened their windows more? And what if people had external shading? Would that help? We did it under current weather, and we looked at what would happen in the 2050s, 2060s climate. And we used 10-year weather files. I'm quite proud of this. I think this is quite good. It's our new method. Let's see what you think. We're calling these recent weather decade files for building simulation. They're easily created. We just take 10 years of weather observations from any location, and we can create a file from those. And they're available in various places. The good thing is they capture the inherent variability of the weather from year to year. Sometimes we get a hot summer, sometimes we get a cool summer. Which one should I model my house under? Let's do them all and see what happens across that range. We also get recent heat waves. As the weather gets hotter, there's a risk our weather files get out of date and don't represent what we're really seeing in our summers. So by using the last 10 years, you get the recent heat waves. You can morph them. There's some standard methods to turn current weather into 2050s or 2060s weather, and we can just use those standard methods. And you get 10 results instead of just 1. And why is that good? Well, 10 results help account for some of this uncertainty around threshold values. If your model result in any one year might be close to the threshold, then in another year it might be below it, in another year it might be above it. And you can start to say interesting things like, well, for this building, no overheating during the past 10 years. That's good, isn't it? That sounds reassuring. Or it might be that overheating occurred during 3 of the last 10 years. Okay, you start to be a bit worried. Or it might be overheating occurred every year in the past 10 years. And then you've got a serious red flag. So we can start to think about how we compare one thing with another with a metric that's less sensitive to uncertainty. It's better than a pass-fail. And hopefully it's easy to compare and easy to understand. So the big question, does whole house retrofit increase overheating? Bit of a table full of numbers. We've got the house, we've got the cross-ventilated house is the top 2 rows, single-sided is the bottom 2 rows. Criterion A just says, does it overheat in the living rooms during the daytime? And criterion B says, does it overheat in the bedrooms on an evening? So we've got A and B for our cross-ventilated house, our single-sided ventilated house, 3 locations in the current climate, the base case, and after whole house retrofit. And then we do the same on the other side, but with mitigation. So what do we learn from this? First of all, overheating can occur in London and sometimes in Manchester. Bit of overheating in London, not very good if you live in London. Only a little bit in Manchester. Glasgow seems quite safe. Retrofit can increase the overheating in the building that is single-sided vented only. So where you don't have cross-vent, the retrofit can actually make the overheating worse. It goes from 4 years to 10 years, 1 year to 3 years, no years to 2 years in Manchester. So if you've only got single-sided vents, could be a problem with retrofit. But the good news, all overheating in all locations, in all homes, was completely mitigated when you increased natural ventilation and provided external shading. So under a current climate, we should not worry about retrofit and overheating. What about in a future climate? Anyone here live in London? Yeah? Oops. So, in the 2050s and 2060s, we're going to see overheating every year in London, often in Manchester and sometimes in Glasgow. Retrofit can increase the overheating when you have single-sided ventilation, again. So those flats that you can only ventilate through one facade, we might have to watch out. But outside of London, overheating was mitigated by increased natural ventilation and external shading. So outside of the southeast, we probably don't have too big a problem with overheating in the future. But I'm afraid in the southeast, it's looking quite likely that there will be a problem. So does whole house retrofit increase overheating? No, that's what our results found. Whole house retrofit with adequate natural ventilation and shading reduced overheating. You're stopping that heat coming in, it's a good thing. There are, though, socio-technical barriers to improving natural ventilation and providing external shading. And we have to address these. You can't just tell people to leave their windows open all day and night. That doesn't work for a lot of people. So there's some space for innovation and new solutions to how we ventilate and how we shade our homes. In London, I think you're going to need mechanical cooling. But the good thing is that when you've whole house retrofitted with all that insulation, that's going to reduce your demand for cooling anyway, so it's no bad thing. So we've got no problem with retrofit and overheating. What about interstitial condensation risk? This way you get moisture between the layers of the building, can cause timber joists to rot, subfloors to collapse. It's quite a bad thing. Internal wall insulation is suspected as being a problem for this. We used a validated hygrothermal modelling software. It's just another modelling tool, a standard one. We modelled a typical solid brick wall. We looked at 2 wind-driven rain locations, London and Manchester, some different thicknesses of insulation. What if we make the U value lower and lower and lower? What happens? Different vapor permeable and vapor impermeable insulation. We used our 10-year weather files again because they're good, and we used a new comparative moisture risk method rather than a pass-fail. So quick aside, our new metric is called moisture risk relative humidity days. It's a little bit like cooling degree days, I suppose. It describes the total time in days that relative humidity exceeds 80% at some critical junction. So this is like between the insulation and the plaster for internal wall insulation. It's comparative rather than absolute, so you can say, well, option A is better than option B, a little bit like my waterproof jacket, and it's calculated for every year of the recent weather decade. So you get wet years, dry years, and all the years in between to give the model that variability. Better than pass-fail, easy to understand. Here's some results. So, this is for the uninsulated wall at the top. And you can see the moisture risk RH days. The more moisture risk RH days there are, the worse it is, so you want none. For the uninsulated wall, you get none. as you start putting insulation to thicker and thicker layers, you get more moisture risk relative humidity days. You get more on average. This shows the median, and then you've got the min-max and the interquartile range to show how it varies year on year on year. So the difference like across the 10 years. So that's the results for all of 10 years, give you this smear. As you add insulation, risk increases, and also the variability between the years increases. I think it's the increasing risk that's more important. One more complicated graph to look at. This is for Manchester. Results were very similar for London. I'm going to start at the top. Wood fibre insulation. I've got my moisture risk relative humidity days up the axis here. The higher this line gets, the worse the risk is. And where you can see that line's got a shadow around it, that's the range across the 10 different years of where the risk was. And this is for the uninsulated wall, and then I'm adding more and more insulation. And then on this graph, I can see the energy savings. So if I put no insulation, I get no energy savings. As I increase the thickness of insulation, I get more energy savings, but my moisture risk goes up as well. Now this is depressing in one way. IWI increases insulation, but maybe there's an opportunity here. There seems to be a bit of an inflection point where you can sort of stop the risk getting out of control and still have quite good energy savings. So maybe we could use thinner internal wall insulation, still get some of the savings, not have all of the risk. I think a bit more work's needed. The wood fibre insulation did better than the vapour permeable insulation did better than the vapour impermeable insulation as well. But there isn't a massive difference. So, does IWI increase interstitial condensation risk? Yes. Installing it makes the walls colder and so wetter. As a building physicist, this isn't a surprise. That's just how things go. But thinner IWI than currently required could be used to reduce heat loss and control moisture risk. More work is needed to decide what's a safe threshold. How many moisture RH days am I prepared to have before I might get a problem? And we need to do field work for that, not modelling. Models are good for some things, but not others. So I want to give you 3 takeaways to finish. Firstly, retrofit will not make homes overheat, so don't be afraid of that, but we must provide adequate, secure, usable ventilation and shading. This is a space for innovation, I think. IWI does increase the risk of interstitial condensation, but perhaps there's an opportunity with thinner IWI where you can get a good balance between energy savings and risk. And then I think that these comparable metrics are more robust than pass-fail metrics, and 10-year weather files help to communicate uncertainty. I'll be interested to know what you think during the Q&A. So thank you for that. I'm going to pass to Dave. Thanks.
Hi, I'm Dave Farmer. I'm a research fellow at the University of Salford, where I run the Salford Energy House. I'm about to pretty much repeat everything the last 3 Daves have told you, but I'm hoping I've got a couple of bits and pieces in here that might be a bit new to you. So I'm going to describe what we did at the University of Salford in our Energy House testing facility during the DEEP project. A lot of this you know already in terms of what DEEP was about. So our main focus here was actually Leeds Beckett did a lot of work in the field, tested a lot of different houses. Fieldwork's inherently complicated in terms of there's lots of dynamic patterns. It's quite difficult to assess the change in thermal performance from one retrofit to another because the weather might change day to day. So the tests have to be over a longer duration. The analysis is more complex. So we decided to do a very detailed study similar to one that Leeds Beckett University did in the laboratory setting, looking at the difference between the piecemeal approach to retrofit and the whole house approach. So I think the definitions here, I think Dave Glue's already discussed what a whole house approach to retrofit is. And it encompasses many things, so it can be what Dave Ransom was talking about, damage to the fabric of the building itself, to the occupants, through, so we've got occupants, damage to the fabric through interstitial condensation, other factors like overheating as well. This project was not intended to look at overheating, interstitial condensation. It was at the risk of surface condensation, so that's whether at junctions or surfaces, and that obviously could lead to mold growth. And the other thing that we did was slightly different to the rest, is that we also thought, hang about, if someone performs a whole house retrofit, it's always thought of in a fabric sense. People think, okay, well, I'll put all this insulation on, but what happens to the heating system that's already there? So how does that impact a pre-existing heating system? If someone retrofits a whole building, does that impact the efficiency and possibly the actual reductions in space heating that you'd expect from a fabric retrofit? So 6 months long test program, 16 months long. You can see the numbers there. It nearly killed us all, but we've just about got there. So the work was done at the Salford Energy House test facility. They built a bigger and not better thing up the road called Energy House 2, so we're now called Energy House 1. It's a replica of a 1920s, pre-1920s end terrace. We used to say it was representative of 7 million houses, but Deep's just told us every house is different, so now it's just representative of the Energy House. But we try to make it as representative as we can. We've got sensors, it's permanently sensed up with over 200 sensors measuring temperatures, internal environments, looking at all energy flows, whether that's each individual heating circuit, whether it's every output from every radiator, from the boiler, from the air source heat pump. So we're constantly monitoring all that data at 1 minute intervals. We've got, as I mentioned, a central heating system. It can be fed by either an air source heat pump or a boiler, gas boiler. We've got infrared heating in there, multitude of heating systems. We can also simulate domestic operation by automating appliance use, openings, etc. So the main thing about the Energy House really is where it's situated in. It's in an environmental chamber. We can repeat the conditions between tests. So essentially, every single test we did in Deep, whether it was looking at fabric thermal performance, all the measurements that they're talking, that Adam, sorry, I was meant to call you Dave. Dave was talking about earlier, a steady state thermal performance measurements. We can create that steady state heat transfer, and we can measure it in the Energy House. So it's we can do that in terms of what we think is more accurately and in less time than was possible in the field. So that's it was kind of almost like validation of some of the work that had been found that Leeds Beckett found in the field. So to do that, we took what we call the piecemeal retrofit approach. So that was what you might see most houses in the field have been done. It's when it's cheaper, when Eco funds something. So it's kind of, we retrofitted each individual element in series, but at each stage of this test program, we measured all the thermal performance measurements, which Leeds Beckett talked about. So that's the heat transfer coefficient. So that's basically your fabric heat loss, the total amount of heat loss through the building fabric. So if you reduce your heat transfer coefficient of your building by 50%, you should be reducing your space heating bills by about 50% as well. So we measured all these air tightness, fabric heat loss at each stage of the process, and this was the piecemeal approach. These are just your standard details. So we didn't look at the interface between junctions. We just allowed what and how each retrofit would normally be specified, and that's how we allowed the contractor to undertake that work. We didn't ask for any kind of special consideration of those details. And then we, following what we call the piecemeal approach for retrofit, so every element has been retrofitted, but we've not addressed the junctions. We then addressed each junction in turn that needed, that hadn't been addressed by the piecemeal retrofit, and measured the fabric performance and heating system performance at each stage until we end up at stage 6D at the bottom there, which essentially that's your whole house approach retrofit if you chuck the kitchen sink at a retrofit. So the piecemeal retrofit, everything was conventional. There was no aerogels, magic paint, pretty much mineral wool, bog standard retrofit. We asked the installer to, we calculate the U values of the existing elements, and then asked the installers to just meet part L1A. We made sure that we were doing that by the specification, And then we asked them to just do it as they would in the field. We didn't ask them to do anything extraordinary. We asked them to price it the amount of time that a retrofit would take in the field. So it wasn't intended to be like a best practice, like trying to reach any fit standard in terms of air tightness levels. It was just trying to replicate what might happen in the field. So you can see, you know, essentially most of it was very, very conventional. The only difference really was the EWI retrofit, still mineral wool, but effectively we had a, it was a system approach, so it was a steel frame system. Initially what happened was the manufacturer came in, they performed a scan of the energy house, built a 3D model. The picture that, if anyone can remember the introduction slide, showed all the steel channels that were prefabricated, cut, all the brick slip cladding as well, came in prefabricated. So essentially this allowed them to come in and what we hoped would retrofit the building a lot quicker than would happen in the field. We think maybe it would probably took about the same time as what a standard EWI retrofit took, but there's certain challenges, as you can see, with scaffolding in terms of working in the energy house. The key thing was, though, that if you look at what you can see here is, which one's a laser? There we go. You can see we left out certain details which would be considered in a whole house approach retrofit. So effectively, this is where you might find below DPC level on a solid wall home. So we didn't insulate that. You can see as well that the EWI kind of only went up to the fascia board. So you didn't, the thermal bridge that Adam was talking about earlier, that wasn't addressed. So effectively what this EWI installation was meant to do was replicate what you might go out and see mainly in the field. We then followed that up with what we call our whole house measures. So those went by simplicity and cost. So the cheapest and quickest one was just insulating below DPC level with the EWI, extending that down below. We then followed that up with a bay window retrofit, and that effectively just almost put EWI over the whole bay window. The reason why that wasn't addressed in the first place was a contractor told us we wouldn't normally bother. It took a lot of effort. And in fact, the bay window retrofit did take a lot of effort because the two side windows of the bay window had to be removed because essentially the geometry of the building had changed. So now they need to be smaller as they were brought out in line. So it was a complex issue which, again, wouldn't be addressed by a standard retrofit. The third one, which was we extended the eaves. So, and this was, I think, the most important one, is you can see that the eaves now being extended, the rafters being extended, and then the insulation layer was brought from to meet the loft insulation and down to meet the external wall insulation at this interface here. And the final one, which is considered the best practice retrofit approach, was moving the external, moving the windows and doors out from the inner leaf of brickwork and into the external wall insulation layer. So effectively, we're trying to look at the difference that each of these, what we call best practice retrofit measures, which you might find in a whole house approach retrofit, what difference these made in terms of heat loss and the risk at junctions. So this essentially here, what we kind of care about in this graph shows us the risk of surface condensation, mold growth at all the junctions in the energy house. So we measured that at 12 different junctions in the energy house. These are based on spot temperature measurements, so you know we can't say this is definitive. And remember, always remember this is a case study, so never take anything I say here as gospel and don't perform any of the measures that I mentioned here. But effectively, we can see that in these two risk categories here, Dave Allinson was talking about having these fixed risk categories, either not a risk or it's not, it is a risk or it isn't. The BRE have this metric called, well, there's a metric called the temperature factor. It relates to the ratio between the surface temperature in the external environment and the internal and external air temperatures. And they say anything below 0.75 is considered a risk of surface condensation, mold growth. Above that, you're fine. It spooks me that if you're at 0.75 that you're never going to have risk of surface condensation, mold growth. But when we looked at our uncertainty analysis, we needed to expand that definition out a bit further. So effectively, we had 3 risk categories. So ideally, we're wanting to aim to be in this low-risk category for the junctions in the house. So you can see we started off with three-quarters of the junctions in the house at high risk of condensation and mold growth. And pretty much nothing really happened until we added the EWI. And at that point, we basically flipped to most junctions being low risk. So the EWI provided us with, essentially kind of created a healthier internal environment. And that's pretty much because external wall insulation interacts with almost every element in the house. So if you're insulating the ground floor, it does nothing for your eaves junction. If you're insulating your roof, it will do nothing for your for the junction between the walls and the external and the ground floor. So following that, we'd done the whole house, the piecemeal retrofit. We then started with the whole house approach measures. That's what we're calling them. And really, yeah, each stage, the first couple of stages, we EWI DPC sorted out one of the risks at the ground floor. The bay window didn't do anything, and then extending eaves got rid of the highest risk junction in the entire house, and I'll discuss that in a little bit more detail next. So at the end of the whole retrofit journey, effectively we had what we're classing as a medium risk left, and that wasn't a fault of the whole house approach method. It was effectively we had the ground floor junction, there was a gap between a joist and the external brickwork, and it was too thin for the installer to put insulation between. So there's a practical issue there. It'll probably happen in other homes, but I say we can't say that's going to happen in all homes. It's not quite representative. So even though we did everything we can say that the whole house approach certainly reduced risks in comparison to the piecemeal approach retrofit. So if we're looking at this eaves extension, you can see here the eaves is now meeting this tacky brick cladding that we got on there. And you can see the insulation now is meeting the insulation layer of the external walls. So on these diagrams here, essentially the red means we're at risk of surface condensation and mold growth. This thermal image here, that was just after the first initial loft insulation retrofit. And you can see here that essentially this eaves junction, the whole of the eaves junction's at risk. And also, with the solid walls and insulated, pretty much most of the solid walls as well. We then put EWI on. This is after the EWI retrofit. And now you can see that the solid walls are pretty good. You know, we can't see any risks on those, so that's good. We've eliminated that risk. But what you can still see along here is this remnants of a risk along the eaves junction here. So we haven't managed to remedy that by the external wall insulation because it left that gap between the loft insulation and the EWI. Finally, we extended the eaves, and now we can see that that junction is pretty much clear, but we've still got this issue here in terms of risk of mold growth and condensation, kind of at the verge detail. So that's where the eaves meets the gable. And if you look on this thermal image, during the deconstruction process, we had a look at that detail, and you can see that it's really difficult to kind of stuff insulation into these small nooks and crannies. So maybe if they hadn't had to take the insulation out at the end, they might have stuffed some foam down there. Maybe that would have done some, wouldn't have might have had caused other problems. But there are always these little issues that no matter how well you specify, that are very difficult to eliminate. So again, we've had that issue with the ground floor with the joist running parallel to the external wall, and again with at this verge detail. So in terms of the air tightness, effectively we didn't really reduce the air tightness by much. The baseline started off below what previous building regs were. We would have met the old building regs for new build by the retrofit, but yeah, the newer standards, is pretty poor in comparison with the new build standards now of 8 meters cubed per meter square at 50 pascals. So the retrofit was only a 15% reduction in air permeability, so a 15% improvement in air tightness. But it actually got worse as we went on through the whole house approach stages, which what that's kind of showing us is that we were trying to convert a whole house approach piecemeal retrofit to a whole house approach retrofit, and all the detail that we were doing between junctions sometimes we were making previous retrofits worse by trying to integrate new retrofits together. So it kind of suggests that doing more retrofits at once might be together might actually be beneficial. We can also see that essentially the previous whole house retrofits of the energy house achieved much greater reductions, and this question rises here is that how repeatable are airtightness retrofits? They really depend upon people sealing up perimeters. These two here were a best practice example for a commercial client. This one here was, let's just set the installer do with typical practice. So I think they raised some questions there about how you can actually predict what your airtightness retrofit will deliver. So yeah, the big thing here is really that, as with similar to Leeds Beckett's findings, it was EWI that reduced the whole house heat loss by effectively, once we'd done that, we'd reduce the whole house heat loss and potentially space heating bills by 50%. But the whole house approach measures, even though they reduced condensation risk at junctions, they didn't actually result in an increase in thermal performance, but the cost raised considerably. So essentially, can we finance these whole house approach measures by saving energy bills? It's unlikely. The main thing that we take away from this is that we notice that some of these measures didn't actually make any difference to the risk at junctions. So actually, it's about picking and choosing which measures are appropriate and which ones are required at a time. I'll just get onto the heating system tests. Essentially, at each stage of the retrofit, we ran a SAP-based heating profile, 2 hours in the morning, 7 hours at night, 21 in the living room, 18 everywhere else. And we measured that with a 4.7 external temperature, which is typical of UK winter temperatures. We tested 2 types of control using this. So we looked at the space heating, gas use and energy and efficiency. And we found that as we progressed through the retrofit, that class 1 controls, which is an on-off control, it's the one that clicks, your standard old school boiler controller, the efficiency decreased throughout the entire retrofit process. So we lost 5% efficiency in our heating system by by the fabric retrofit, resulting in essentially the system being oversized. So it was oversized for its heat loss. The modulating controller, a class 5 controller, was not impacted by the retrofit. So it suggests that actually if your boiler is capable of modulation, a class 5 controller might be a good thing to switch to after a retrofit, because it might help you in terms of not losing system efficiency, because without it, this house here with a class 1 controller, its gas use would have been 6% greater than what it should have been if its central heating system was appropriate size for its heat loss. So what can you do about heating systems that aren't suitable for modulating controllers? We reduce the flow temperature of the central heating system based on the new heat load of the house. So we calculate the heat load and we adjusted the flow temperature to provide the heat input required for its new fabric heat loss. And you can see now what was previously 70 degrees C, at 50 degrees C, it's increased the efficiency of the heating system, restoring those losses. And this isn't what the government are telling you to do by turning your thermostat, your boiler flow temperature down by 10 degrees. This is an informed calculation of your heat load. So you're not going to struggle to keep your house warm at colder temperatures or impact too much on heat up times. So it's quite important. So houses with older boilers that you can't put modulating control, we're suggesting that we need some good tools to inform householders what the heat load of their house is, what the heat loss is, and what temperature setting they should set their boiler, because effectively there's a lot of missing gains here that they could be achieving. And effectively as well, if you don't consider your heating system in your whole house retrofit, you could be undermining some of the gains in fabric. That's pretty much what I said. Oh, and that's Grant. He nearly died doing this. We worked his socks off. So I want to thank him. Right, are we doing... applause. I get the applause. going that.
Yep, they're all on, Helena, yeah.
Hello, Max.
Brilliant. Okay, thanks everybody. Thanks speakers for some really informative and interesting presentations. So there's lots and lots of questions. I just wanted to kick off very quickly, I suppose, just to provide a little bit of closing context for the audience and framing their questions. What's next from this research?
We've got to publish it, for sure. And what we're trying to do is synthesize all of that mess into one big, nice story. So what have we done to improve things that... What messages can we give government so that they can improve policy? What messages can we give to industry so that they can improve practice? So I think that's what we're looking at now. And then some of the individual findings have got really nice lead-on opportunities for future research. For instance, some of the things around thresholds and changing the way in which we use weather data to improve models further. And this is opening up tons of new research opportunities for us.
Would any of you like to pinpoint a specific research opportunity from your area that you would like to explore further?
Yeah, I think so. For moisture risk, there's this really interesting idea that you might still be able to apply IWI without to some kind of safe level. But what does a safe level look like? That's a really difficult question, actually. And moisture takes so many years to evolve. So I think that's going to remain a tricky longer-term question that needs, more time.
I think expanding on that, one thing we've seen is that some of those whole house approach measures, it's very difficult for a specifier to know whether they're required or not. And so moisture risk, identifying moisture risk, I think that's something that I want to see more tools for people to be able to identify those and go into a house, look at it, because one of the things that's coming out of DEEP is that every house is different, and every risk, risks will be different in every house. And so some of these measures are incredibly expensive in comparison to the payback times. So we need to identify which houses require these certain measures, and this is, I think, going to tools. It's tools for moisture risk. I think those are what's there's a big opportunity here for somebody to, either it's academics or the commercial sphere, to actually say, okay, how can we go into a house, identify the houses where there is a risk, and which ones need these additional measures, and actually can we just leave some homes alone and not bother with those. So I think that's certainly where we'd like to follow up. And
Adam, did you have anything that you wanted to
Yeah, so I talked in my presentation about how a lot of the measures that we installed didn't have a detectable impact on heat loss. But in terms of the physics of the house, it should have been having some impact. It's just that the measurement we were using wasn't sensitive enough to detect it. And we were using basically the most sensitive measure possible. You could, in theory, detect the impact of something like loft insulation if you increase your sample size. If you, for example, did it in 100 homes and looked at it as an ensemble, you could detect the impact. So there's this interplay between how precise your measurement method is, i.e. what your uncertainty is, and the sample size of the cohort that you're measuring. But nobody really knows what that interplay is. How big does your sample size have to be if you've got a precise measurement method, and if you've got an imprecise measurement method? And that's interesting, I think, from the perspective of the government, who are trying to sort of get a handle on this. There's measurement methods for HDC out there which are less precise. So they probably can't detect anything on an individual house basis, but maybe they can if you deploy them to a large sample. And it'd be interesting to know how big that sample has to be.
Thank you very much. I'd like to open questions to the floor, if anybody has it. If you could raise your hand. John's got the roving mic. Just because we're recording it, if you just wait till you've got the mic before speaking into it, and then perhaps introduce yourself as well. And then your question, please.
Hello, my name is Jonathan Rosenberg, and back in the 90s, back in North Paddington, we took over about 200 Victorian houses, and in the early mid-90s embarked on a whole house retrofit program, full strip out, and all the rest of it. So, first of all, I'm absolutely amazed and gobsmacked by these results because they confirm my deepest prejudices, which have been learned through lived experience. And the architect that we had, and I have to say his name, Hilary Chambers, his mantra was insulation, ventilation. And the ventilation had to be passive. It had to be as much as possible. So when we did up the homes, I mean, obviously the basement floors came up with the insulation there, they're off now. Internal wall insulation, 50mm polystyrene behind the plasterboard. No draft proofing. Anywhere there was a chimney breast, he slapped in a grill. So we get quite a good draft, to put it mildly. Sash windows, double glazed, sensitive to the Victorian properties and everything. We do not have any mould in any of those properties, so far as I can tell. It would be impossible because the ventilation is so good. We do not rely on mechanical ventilation, or, if you like, tenants blocking things up and all the rest of it, because the way it's all designed. So I suppose the big question I wanted to ask, because we've recently done a scheme where we were putting in some extra homes on top of some purpose-built stuff from the 60s. And the objective was to completely achieve a 100% seal, and then with mechanical ventilation. Well, it's turned into a nightmare because the mechanical ventilation, well, I'm not going to go through the list, but I'm sure people know about the challenges faced with that. Amazingly, thank God, the contractor did not achieve a 100% seal. So far, nobody has died from asphyxiation in any of the bedrooms that we built. So what I want to ask is, when we're dealing, because I'm in North Paddington, which is one of the greatest population densities of anywhere in the UK, all in solid wall Victorian, late Victorian houses. And I'm amazed to see the external wall approach, which could be used on back additions, of course. But what I want to ask is it really sustainable to go for sealing places up so that there is no fresh air coming in unless it's dependent on mechanical ventilation?
Thank you very much for your question. Do you want to put a bit-
Yeah, I think it's quite a quick one, really. I mean, you'll see we didn't look at purpose-provided ventilation as part of the retrofit tests that we were doing because we required some kind of longitudinal study. It was outside the scope. But when we talk, there's two different types of what you're talking about here. Sealing up shouldn't be stopping fresh air. So that's what vents are for. So your fresh air should come direct from outside, whether it's mechanical or natural. What we're trying to get rid of is the drafts that come through the cracks and the gaps and the floors where the mice poo and the spiders live and all of that. That's not really fresh air. You shouldn't be relying on that. So sealing all of that up is fine. That's okay. You can do that. You should always do, well, we would always recommend you do tests to make sure that if you do drop below a certain level, you add in additional ventilation. That's all in the regs. That's a whole part of the whole house approach to retrofit, that all things that are funded now have to do to say that they've achieved the standard. So that sort of thing, that shouldn't happen. There should always be enough ventilation alongside any insulation that's put into a home. So.
There's a question at the back.
Hello, I'm Nigel Coney-Bear. It's just a question on the interstitial condensation. On the interstitial condensation, from experience where we work from, you have to take into account the orientation, solar orientation of the building, and obviously what the building's all about. I agree with you in as much that there could be a case there that you have thinner and thicker walls of insulation, so north facing actually have a thicker insulation and a south facing have a thinner one, to let the whole building be a full concept rather than a carte blanche if pass or fail, and that's where we come from. It is that going to be taken on board with your calculations?
Yeah, so we calculated these comparative risk metrics for different orientations as well. And the results were quite interesting because it wasn't always the orientation that we thought that was the one with the highest risk. So it's not just wind-driven rain, it's also, of course, exposure to the sun and the ability for the wall to dry as well. So I think this is a really interesting area, and reflecting on Dave's comment earlier, developing simple to use tools that might give you a rapid assessment in a cost-effective way of where the biggest risk is on which walls, in a comparative sense, could be one way forward. So, yeah, I think I've just agreed with what you said. Is that right?
Actually, I would say I didn't have a chance. I should have. Jonathan, did that answer your question? Did David's response answer your
I
question?
think it's the issue is in social housing. In social housing, we've got to the stage where you can't go around and say to people, no, you shouldn't be putting your washing here and all this stuff. I mean, frankly, that's batty. So we've ended up in a rather strange place, and my feeling in the end is that if you're managing social housing and if you're retrofitting it and all the rest of it, you have to, all of this stuff has to take into account how people live, and if you're not supposed to go around telling people they shouldn't be hanging up their washing inside, well, I'm sorry, but you're going to have to design the retrofit differently. On the other hand, it might be a good idea to tell people to do a bit less of that and so on, or it might be an idea to ensure you've got sufficient passive ventilation so that you do not rely on the tenant managing the mechanical ventilation. Because the problem is they switch it off and say, well, I can't afford the electricity bill. You want to go around and explain it?
I think there's a wider point there about engagement with the community, isn't there? There's a point about the education side of it, but in the first instance, getting to a point where you can get into people's homes to retrofit them for them, there's a communication piece there about the benefits as well, isn't there? So I think that the people element is quite key as well.
I think there's pretty limited scope for, well, if full MVHR in most retrofits isn't really going to happen, is it? But you're always going to have mechanical, people are going to think mechanical ventilation is like a silver bullet, aren't they? My concern with it is what happens if, okay, people switch it off, or someone says it's making it cold and they're relying on that for positive input ventilation, or the filters get clogged and no one ever does anything. So I think, like, risk-wise, I think it's really quite important that maybe we design things that if no one touched it, it still works. You notice if your air source heat pump stops working or your boiler stops working. Hopefully we'll start noticing whether they're working effectively or not. These are some things that, efficiency, more and more data get out of these things, and more we'll know whether they're efficient or not. Perhaps, later down the line, if some of these mechanical ventilation systems are not providing the decent air quality, someone might find out about it. But for me, I always think if you've got a system, and if you notice it not working, then you could do something about it. But some of these, at the moment, there's too much risk asking some people to deal with those.
A supplementary question, because it's the experience that we've had of this 30 years of having done the whole house retrofit is that actually, when you consider the condition of the properties when we approached them, thermal insulation was just one of many things on the list. But, in the end, what's going on is comfort. This issue of people being able to live in a Victorian house in comfort. And that doesn't mean, vastly lowered fuel bill. But it makes a huge difference in terms of, people's personal experience of living in the home, the ability to retain heat, and indeed in this sort of weather, the ability to keep out the cold. I can achieve a 6-degree difference between inside and outside, by managing with the curtains and the doors and so on. So I mean, the other reflection I want to make is that I think it's extraordinary if this is indeed true, that it's only the wall insulation, whether internal or external, which seems to make any significant difference. What I wonder there is whether you actually have any explanations for why that should be the case.
I mean, for the energy house test, that was a end terrace. So effectively, the vast majority of its surface area was external wall, and as a starting U value, it's pretty high. So if you're getting something that's down from 1.6 down to 0.3 roughly, and it represents almost 3/4 of your surface area, it's going to make a big difference. But even for mid-terrace, I think some of the modelling has found that even... Pardon?
I'm thinking about the back additions where you've got at least 2 external walls.
I think you've done some of that modelling stuff Leeds Beckett did. actually looked at mid-terraces and
Yeah, we
found
measured
something like-
lots of different types of homes with the different wall areas, and it comes down to the surface area and the starting U value. So lofts already have a pretty good U value. The solid walls have got a really bad U value. So it's just the physics of it.
Thank you. I think we've got a question at the back over there. If you wouldn't mind holding on for the microphone, please.
Thanks very much. Thank you, sorry for dropping my phone. I'm Alfie Stroud, I work for Historic England, so we obviously have a big interest in solid-walled houses and how we retrofit them. And I have lots of colleagues who do think about the technical things much more. I'm actually a historian, so I'm very much not a numbers person, but I'm very interested from a sort of planning point of view, and to ask a question on the kind of large scale and about how this might be scaled up. You've pointed out how important terraced houses are as a typology in Britain. So something that plays on my mind is presumably the party walls between all the houses in the terrace are a critical point, and especially in relation to external wall insulation. Presumably that can't happen on one bit of a terrace. You know, to be effective, it needs to happen to the whole terrace. So in a context where we're still relying fundamentally on individual householders to do the retrofit works, how does that work? That's a sort of question, comment.
I think I speak for everyone here when I say we all hate party walls. They make our work very difficult, and if I could just study detached homes, I would. They do cause issues. If you wanted to retrofit a series of terraced homes, ideally, do them all at the same time. If you don't, you do get some interesting effects happening because the junctions can start behaving in ways you might not expect. If I insulate my house and I'm in a terraced home, I might decrease the moisture risk on my junction, but I might actually increase the moisture risk on my neighbour. So these are issues that we've known about for a little while. We don't have a solution to them. We don't know what the legal ramifications of doing something like that are, but it's stuff that we consider a lot, and we will continue to work on them.
In terms of the energy house work, we only insulated one of the, so it's got a neighbour. We've done the IWI retrofit before, and yes, it increases the moisture risk in the neighbour if you only insulate IWI on your external one. It gets even worse if you don't then insulate the return. But if you're actually just, we didn't find on this project actually EWI that stopped at the party wall line actually had any problems in terms of mould and condensation for the neighbour on this occasion. I think it's just the thing that essentially if you're pepper potting, it just adds the complexity and the cost of doing the retrofit, doesn't it?
We did actually insulate 2 homes on the same street, one in the middle and one at the end, and you get what I guess we all really recognise as the penguin effect. So the home in the middle, it was already an EPC band C because it had such a low amount of external surface area, and the one on the end we had to insulate in order to get it up to a C. So if you have to do only a few, you could kind of just do the ends if you're short on budget.
There's another question, but just the other side of the column. Thank you.
Thank you. I'm Ossie Lane. I have the misfortune of living in a Victorian solid wall terrace. So I was hoping to come here, and if you guys need some further sample surveys, I'm available. One of the things I was interested in, you've done these studies. You're just about to publish a report. One of the things I'm interested in is what are you going to now consider how these changes actually pan out over the next few years, taking into account the behaviour of people, as this gentleman said earlier, how they live in the houses, how they maintain them. We've got environmental impacts of flooding, heat waves. Typically the houses in my street are very shallow foundations, so at risk of heave and subsidence, and the impacted costs of doing repairs to retrofitted homes. I work for a social housing provider. We're going to be throwing a lot of money at retrofitting, and what are the ongoing costs going to be? Will you be going back to these houses in 10 years' time and seeing how they fared?
We'd love to, but we don't have the funding, and it wasn't part of the project, and it's now back with the social housing providers. And if they want us to come back and check that would be great. But I think you've raised a really neat point, because what we haven't talked about is costs so much here. And what obviously we know the costs of the ones that we did, and we can't say that it's totally representative, because they knew we were paying. We asked them to do it wrong first and then do it right again, and so we've had to kind of be a bit clever around, understanding what it might have been if they were doing the whole street versus just our house, which is what we had. So we're not perfectly representative, but we have these extra costs. Every single time we did a retrofit, almost, the stuff goes wrong, or there's something that we had to do first or change. It could be the plumbing, it could be extra scaffolding, it could be clearing, it could be cleaning because you've made such a mess, all of these different things, rebuilding a garden wall that was too close. And so we've got some numbers on that now. We think there might, on average, across our sample of 14 homes, of the total cost, it was about 25% was nothing to do with the retrofit, kind of extras that was not intended to be spent at all. And there's a couple of things I want to say about that. One is that the retrofit's fault? This needed doing anyway. You had a roof that was leaking. So we've said it's part of the retrofit cost because we had to repair the roof. But what we've done there is we've improved the building fabric, we've improved the longevity of that building structure. And is that fair to say that it would cost, this retrofit cost a lot? Goodness me. Actually, it's a building maintenance cost. And so what we're doing by retrofitting homes is prying into all of these things that are hidden. So you can see that as a negative because you're going to spend more money, but you could actually see that as a really big positive. So the retrofit drive could incidentally really start to improve the quality of these homes that are getting retrofitted because you spot all of these, problems. I don't know if there was a second point, can't remember.
Does that address your point? Great. I think we're going to have to start to wrap up. There's another question in the back corner there, and then we might have time for one more afterwards.
Thank you. I was just wondering how, or whether there is any intention of using all this knowledge that's been learned with these studies to inform the education of future architects or possibly even current architects, so that they get skilled and more knowledgeable, because I've studied in Austria and in the UK. Building physics in Austria is part of the core curriculum for architects. It's practically unheard of at university education, at least in the one that I went to, which is a great shame, because I think we could all learn, all those in the building industry should be more skilled and knowledgeable about this.
You're all in academia. Is there anyone who particularly would like to take that one?
At Loughborough University, we have an architecture course where building physicists, of course, teach the architects, but I didn't want to just plug that. I think you make a really good point, and I think we can do more in this space. Yeah.
I'd say at Leeds Beckett University, there's a School of Architecture. We're not in the School of Architecture. We do building physics and do science around how you make buildings. So I agree wholeheartedly, and I think that stems not just with building physicists and architects, but engineers and architects. There's a siloed approach historically through the built environment landscape or societies, which it's not just, it doesn't just affect us, but we feel it very much. A lot of these things have got relatively simple fixes if you get it right at the design stage. And that would be addressed, I think, by what you're suggesting. Where I think architecture is getting really good is once it's finished, they don't just walk away now, or often they will keep a connection, some kind of post-occupancy evaluation. So I think we're getting better at that final stage bit, but we do still need to get better at that design stage bit as well.
And I think as well, they need to speak to the people who actually do the job. Because we can speak to the architects, but I actually find it's quite useful to speak to the installer, and then you actually learn something from them, because we can pontificate about what should be done. But actually, when you realise why certain things weren't done, you can then start to understand and propose solutions. So I think it's very important that, as well, that we can inform the architects, but as well the architects need to speak to the people who actually put the things in and specify that relation between the specifier and the installer. I think is really important.
I think the clue is kind of in the name, isn't it? It's a whole house approach, it's a holistic approach, it's a systems approach to buildings, and not only domestic but non-domestic as well. Increasingly it needs to be seen as a system, and so that interdisciplinarity really needs to come through and start to come through in the teaching as well. Are there any more questions? One last question. I think you popped your hand up first.
I had two, last two very quick ones. Hi, I'm Rebecca Archer. The first question I had was to the last David about the heating of the house. And you said about kind of needing to turn the temperature down if you have a traditional boiler because it's more efficient. Is that kind of helped if you change to an air source heat pump? Does it work better in a retrofitted house just because of the lower energy demand? Does that make it more efficient, or is it just that it's feasible to use in a retrofitted house because it's not powerful enough if you don't do the retrofits?
So we did, as part of DEEP, do some air source heat pump testing. I wasn't, I was going to keep that under the lid really, but so we were about to find out when installing an air source heat pump would be viable along that journey. So you saw that piecemeal retrofit journey, and we wanted to find out at what point, and this is about financial viability, not carbon at the moment, because people can say, okay, well, I'm saving carbon, but if it's costing them more, they're not bothered. Most people, I'm assuming. So anyway, we tested the air source heat pump, loads of stages. We got to put the EWY on, do the whole house approach retrofit, and we did all our tests, and DEEP was primarily fabric performance test anyway, so we analysed the data, and the coefficient of performance went down from, we got a new heat pump in, by the way, because appropriate size, went down from about 3.4 to about 1.9. And then we looked at what the reason for that was, is that the installer had come in and hooked it up the wrong way round. So the air source heat pump was thinking that the water coming back from the house was getting warmer than when it went out. And so a boiler wouldn't mind so much. But at no point, it heated the house fine, it heated exactly the same as before, but at no point did that unit ever tell us we've set up wrong, and we trusted the installer. We noticed that it was wrong because it was costing a third more than what it should be, or even more than what it should be. But if someone sat there with an energy bill and it's coming in, it's almost a third to a half higher than what it should be, they're not going to know that. It's only because we said, look, let's investigate the problem here. So we, based on the coefficient performance we achieved before solid wall insulation, we're assuming that in this instance, as an end terrace, you needed the solid wall insulation before the air source heat pump became financially viable. That's, But before that, gas outstripped it. But the interesting thing is as well is that at the beginning of DEEP, actually because the ratio between the gas price and electricity price keeps changing, the closer the gas and electricity get, the more viable it is for an air source heat pump. So there are market factors as well as in terms of fabric thermal performance to address.
Great, thank you.
Would you mind, I think we're getting tight for time now, would you mind following up afterwards? I think
there's drinks.
It's all right to close now. I would definitely encourage you to take advantage of the drinks that have been provided by Leeds Beckett University this evening, kindly by them. And also, if you can, take a little moment to go upstairs and have a look at the exhibition as well, if you haven't already. It's really interesting. Could you just all join me, please, in saying a round of applause for our speakers?